Hello dear students, welcome to the lecture 6 of Security of Information Systems. So today's topic is computer security, and let's start with the lecture overview. So we will see secure computer architectures, virtualization architectures, trusted computing. Okay.
System and communication security.
So according to the
Gene Spafford. Using encryption on the internet is the equivalent of arranging an armored car to deliver credit card information from someone living in a cardboard box to someone living on a park bench.
okay. So the
Vulnerabilities of the PC today.
you see what vulnerabilities there are. Vulnerable to software attacks, which are like PCI Express to graphic cards and high-speed USB ports and such things, as you can see.
Vulnerabilities of the PC today.
Okay, so this is input-output bus. So what is input-output bus?
In computer architecture, a bus 1, a contraction of the Latin omnibus, citation needed, and historically also called data highway 2, is a communication system that transfers data between components inside a computer, or between computers. This expression covers all related hardware components, wire, optical fiber, etc., and software, including communication protocols. 3.
Okay, so this is input-output bus of the system. And so let's see. You see access to protected memory through DMA. This is a vulnerability. Okay, let's look for it on the internet. And okay, you see there is DMA attack.
A DMA attack is a type of side-channel attack in computer security, in which an attacker can penetrate a computer or other device, by exploiting the presence of high-speed expansion ports that permit direct memory access, DMA.
So DMA is direct memory access.
DMA is included in a number of connections, because it lets a connected device, such as a camcorder, network card, storage device or other useful accessory or internal PC card, transfer data between itself and the computer at the maximum speed possible, by using direct hardware access to read or write directly to main memory without any operating system supervision or interaction. The legitimate uses of such devices have led to wide adoption of DMA accessories and connections, but an attacker can equally use the same facility to create an accessory that will connect using the same port, and can then potentially gain direct access to part or all of the physical memory address space of the computer, bypassing all OS security mechanisms and any lock screen, to read all that the computer is doing, steal data or cryptographic keys, install or run spyware and other exploits, or modify the system to allow backdoors or other malware. Preventing physical connections to such ports will prevent DMA attacks. On many computers, the connections implementing DMA can also be disabled within the BIOS or UEFI if unused, which depending on the device can nullify or reduce the potential for this type of exploit.
Okay, so this type of exploit is extremely hard. Why? Because it requires physical connections. Okay, and if you have physical access to a computer, you can already do many other stuff as well. Okay, so USB controller, mouse, keyboard. This is one of the most common ones, which are keyboards, keyloggers. With keyloggers, hackers can read your mouse input and keyboard input. Therefore, they can steal your passwords and other sensitive information and such. Okay, so there is access to graphic frame buffer attack. Okay, I wonder if there is any good article about this. Let's try like this. Okay, I couldn't find, but I will just pass it. And there is insert malicious code into the file that will be executed later. This is also one of the most common ones because you see, when you download a file from torrent sites or from file sharing sites, they may insert a hidden code, a malicious code into those files, those exe files or data files that will be read by that exe, and therefore it is extremely dangerous to download files from uh, let's say unofficial sources. Therefore, this is one of the most common way of hacking PCs in today. And there is access to process memory. This is also one of the another most common way. Also, this is not only applied to the computers. In many of the other devices, this is the source of hacking in most cases. For example, I think recently there was a bug that let hackers exploit buffer overflow of the browser in iOS or Android. Okay. Okay, I think this one was it. Okay, here.
Malicious mails that trigger the flaw work by consuming device memory and then exploiting a heap overflow, which is a type of buffer overflow that exploits an allocation flaw in memory reserved for dynamic operations. By filling the heap with junk data, the exploit is able to inject malicious code that then gets executed. The code triggers strings that include 4141.41, which are commonly used by exploit developers. The researchers believe the exploit then deletes the mail.
Okay, so you see, this is a real case, and the article date is pretty recent. It was in 22 April 2020. Okay, so let's get more idea about the attack.
A critical iPhone and iPad bug that lurked for 8 years may be under active attack. Malicious emails require little or no interaction, exploits active since at least 2018.
So you see no interaction, which means that this is the most dangerous type of vulnerability of exploit, because user doesn't have to do anything. They can get infected totally remotely without being doing anything, without having any idea. Okay, let me zoom in a bit.
A critical bug that has lurked in iPhones and iPads for 8 years appears to be under active attack by sophisticated hackers to hack the devices of high-profile targets, a security firm reported on Wednesday.
So since this was only targeting high-profile targets, it was unnoticed for 8 years. Okay.
The exploit is triggered by sending booby-trapped emails that, in some cases, require no interaction at all and, in other cases, require only that a user open the message, researchers from SECourses said in a post. The malicious emails allow attackers to run code in the context of the default mail apps, which make it possible to read, modify, or delete messages. The researchers suspect the attackers are combining the zero-day with a separate exploit that gives full control over the device. The vulnerability dates back to iOS 6 released in 2012. Attackers have been exploiting the bug since 2018 and possibly earlier.
So you are wondering what is 0 day. Okay.
A zero-day, also known as zero-day, vulnerability is a computer software vulnerability that is unknown to those who should be interested in mitigating the vulnerability, including the vendor of the target software. Until the vulnerability is mitigated, hackers can exploit it to adversely affect computer programs, data, additional computers or a network. An exploit directed at a zero-day is called a zero-day exploit, or zero-day attack. The term zero-day originally referred to the number of days since a new piece of software was released to the public, so zero-day software was software that had been obtained by hacking into a developer's computer before release. Eventually the term was applied to the vulnerabilities that allowed this hacking, and to the number of days that the vendor has had to fix them. 2, 3, 4. Once the vendor learns of the vulnerability, the vendor will usually create patches or advise workarounds to mitigate it. The more recently that the vendor has become aware of the vulnerability, the more likely that no fix or mitigation has been developed. Even after a fix is developed, the fewer the days since then, the higher the probability that an attack against the afflicted software will be successful, because not every user of that software will have applied the fix. For zero-day exploits, unless the vulnerability is inadvertently fixed, e.g. by an unrelated update that happens to fix the vulnerability, the probability that a user has applied a vendor-supplied patch that fixes the problem is zero, so the exploit would remain available. Zero-day attacks are a severe threat. 5.
Okay, so this is the generic term of exploits. Okay, and you can read more about that here. And let's continue to our recent memory error, memory exploit in iOS and iPhone and iPad. So enormous scope.
With very limited data, we were able to see that at least 6 organizations were impacted by this vulnerability, and the full scope of abuse of this vulnerability is enormous, SECourses researchers wrote. We are confident that a patch must be provided for such issues with public triggers ASAP.
So let's see the targets.
Targets from the 6 organizations include individuals from a Fortune 500 organization in North America, an executive from a carrier in Japan, a VIP from Germany, managed security services providers in Saudi Arabia and Israel, a journalist in Europe suspected, an executive from a Swiss enterprise. Zero days are vulnerabilities that are known to attackers but not the manufacturer or the general public, are rarely exploited in the wild against users of iPhones and iPads. Some of the only known incidents: a 2016 attack that installed spyware on the phone of a dissident in the United Arab Emirates, a WhatsApp exploit in May of last year that was transmitted with a simple phone call, and attacks that Google disclosed last August.
Okay. So let's read here again.
Malicious mails that trigger the flaw work by consuming device memory and then exploiting a heap overflow, which is a type of buffer overflow that exploits an allocation flaw in memory reserved for dynamic operations. By filling the heap with junk data, the exploit is able to inject malicious code that then gets executed. The code triggers strings that include 4141.41, which are commonly used by exploit developers. The researchers believe the exploit then deletes the mail. A protection known as address space layout randomization prevents attackers from knowing the memory location of this code and thus executing in a way that takes control of the device. As a result, the device or application merely crashes. To overcome this security measure, attackers must exploit a separate bug that reveals the hidden memory location. Little or no sign of attack. The malicious mails need not be prohibitively large. Normal size emails can consume enough RAM using rich text format documents, multi-part content, or other methods. Other than a temporary device slowdown, targets running iOS 13 aren't likely to notice any signs that they're under attack. In the event that the exploit fails on a device running iOS 12, meanwhile, the device will show a message that says, "This message has no content." SECourses said the attacks are narrowly targeted but provided only limited clues about the hackers carrying them out or targets who were on the receiving end. We believe that these attacks are correlative with at least one nation-state threat operator or a nation-state that purchased the exploit from a third-party researcher in a proof-of-concept (POC) grade and used as is or with minor modifications, hence the 4141.41 strings. SECourses researchers wrote, "While SECourses refrain from attributing these attacks to a specific threat actor, we are aware that at least one hackers for hire organization is selling exploits using vulnerabilities that leverage email addresses as a main identifier." The most visible third-party organization selling advanced smartphone exploits is Israel-based NSO Group, whose iOS and Android exploits over the past year have been found being used against activists, Facebook users, and undisclosed targets. NSO Group has come under sharp criticism for selling its wares in countries with poor human rights records. In recent months, the company has vowed to serve only organizations with better track records. It's generally against security community norms to disclose vulnerabilities without giving manufacturers time to release security patches. SECourses said it released its research ahead of a general release fix because the 0-day alone isn't enough to infect phones. The bugs had already been mentioned in the beta release, and the urgency created by the 6 organizations the firm believes are under active attack.
Okay, so now we have a very good idea about access to process memory. Most of the attacks are carried this way. This is true. Therefore, having good memory protection, memory space protection is extremely important and also complex and perhaps hard to achieve.
Approaches to strengthening platform security. Harden the operating system. SE Security Enhanced Linux, Trusted Solaris, Windows the 8th of July 10.
So this is actually Windows 7, 8 and 10. Okay. So with Windows 7, Microsoft started to improve their platform security. Of course, it is the best at the moment with Windows 10.
Add security features to the CPU. Protection layers, no execute, ASLR.
So what is no execute? Okay. Okay.
The NX bit no execute is a technology used in CPUs to segregate areas of memory for use by either storage of processor instructions code or for storage of data, a feature normally only found in Harvard architecture processors. However, the NX bit is being increasingly used in conventional von Neumann architecture processors for security reasons. An operating system with support for the NX bit may mark certain areas of memory as non-executable. The processor will then refuse to execute any code residing in these areas of memory. The general technique, known as executable space protection, also called write XOR execute, is used to prevent certain types of malicious software from taking over computers by inserting their code into another program's data storage area and running their own code from within this section. One class of such attacks is known as the buffer overflow attack. Intel markets the feature as the XD bit execute disable. Advanced Micro Devices (AMD) uses the marketing term Enhanced Virus Protection (EVP) citation needed. The ARM architecture refers to the feature, which was introduced in ARMv6, as XN execute never. 1. The term NX bit itself is sometimes used to describe similar technologies in other processors.
Okay, so there is more information if you are interested in that. And there is ASLR. Okay. So we have seen this in the article, if you remember, in just a few minutes ago.
Address Space Layout Randomization (ASLR) is a computer security technique involved in preventing exploitation of memory corruption vulnerabilities. In order to prevent an attacker from reliably jumping to, for example, a particular exploited function in memory, ASLR randomly arranges the address space positions of key data areas of a process, including the base of the executable and the positions of the stack, heap and libraries.
Okay. Okay, I will take a pause for a moment. Okay. So,
Virtualization technology separates processes by separating virtual systems.
this is commonly used technology.
Trusted computing adds secure hardware to the commodity platform. EGTPM, Trusted Platform Module. Rely on secure hardware external to commodity platform. Smart cards. Hardware tokens. OS protections, launching a process.
Okay, so now we are going to see operation system level protections.
When the system runs an executable, the code and the data of the executable are loaded into the random access memory. The OS analyzes the code and also copies the required dependencies and the necessary OS API files into the memory. Each process has an own virtual address space, where all necessary code and data are loaded. The process can access only its own virtual address space by CPU instructions.
So each process is encapsulated within their own private memory sections. Therefore, they are not able to, let's say, modify other processes' memory. Okay. So we can see how it is done here. Main memory and certain part of the memory is assigned to a certain process.
OS protections, process virtual address space. The process code can access its own address space, but this addressing is different from the global physical addressing. Each process has the maximum addressable memory range, a virtual memory in a virtual address space. This is 232, 4 gigabytes, i.e. in 32-bit systems hexadecimal 0000000xFFFFFFFF.
Okay. In a 32-bit operation system, a single process can hold up to maximum 4 GB of data because with 32 bits you can maximum allocate 4 GB of RAM memory. Okay. If you wonder why,
There seems to be a lot of confusion in the industry about what's commonly called the Windows 4 GB memory limit. When talking about performance tuning and server sizing, people are quick to mention the fact that an application on a 32-bit Windows system can only access 4 GB of memory. But what exactly does this mean? By definition, a 32-bit processor uses 32 bits to refer to the location of each byte of memory. 2 to the power of 32 equals 4.2 billion, which means a memory address that's 32 bits long can only refer to 4.2 billion unique locations, i.e. 4 gigabytes. In the 32-bit Windows world, each application has its own virtual 4 gigabytes memory space. This means that each application functions as if it has a flat 4 gigabytes of memory, and the system's memory manager keeps track of memory mapping, which applications are using which memory, page file management, and so on. This 4 gigabytes space is evenly divided into two parts, with 2 gigabytes dedicated for kernel usage, and 2 gigabytes left for application usage. Each application gets its own 2 gigabytes, but all applications have to share the same 2 gigabytes kernel space.
okay, there is some more information.
x86 processor hardware architecture is augmented with additional address lines used to select the additional memory, so physical address size increases from 32 bits to 36 bits. This, theoretically, increases maximum physical memory size from 4 gigabytes to 64 gigabytes. The 32-bit size of the virtual address is not changed, so regular application software continues to use instructions with 32-bit addresses and, in a flat memory model, is limited to 4 gigabytes of virtual address space. The operating system uses page tables to map this 4 GB address space into the 64 gigabytes of physical memory. The mapping is typically applied differently for each process. In this way, the extra memory.
Okay, sorry about the interruption. I will repeat.
x86 processor hardware architecture is augmented with additional address lines used to select the additional memory, so physical address size increases from 32 bits to 36 bits. This, theoretically, increases maximum physical memory size from 4 gigabytes to 64 gigabytes. The 32-bit size of the virtual address is not changed, so regular application software continues to use instructions with 32-bit addresses and, in a flat memory model, is limited to 4 gigabytes of virtual address space. The operating system uses page tables to map this 4 GB address space into the 64 gigabytes of physical memory. The mapping is typically applied differently for each process. In this way, the extra memory is useful even though no single regular application can access it all simultaneously.
Okay. So there is another important information here.
However, there are techniques like physical address extension (PAE) that allow a 32-bit OS to address more than 4 GB of RAM. Drastically oversimplifying the process, the OS maps each process in a certain part of the memory, called a page table. Each process is still limited to 4 GB, but this allows the OS to address as much more memory than only 4 GB. The 32-bit version of Windows Server 2003 Datacenter Edition, for example, supports up to 64 GB of RAM.
Okay. Anyway, let's continue.
To ensure the correct memory operations, the OS has to provide a runtime address translation between virtual memory to the physical memory.
Okay.
OS protections, process virtual address space.
We continue with this one.
Because of this way of operation, the OS provides two protections by design. The program code that is executed cannot access the physical memory directly. We cannot write code to access physical memory in none of the programming languages.
Okay. Actually, in my programming life over, let's say, 15 years, I have never written a code to manage memory address. Okay. It was always done by the compiler, by the runtime, and probably you will never also work with this stuff. However, this is important for security. You see, the hackers, exploiters, tries to find exploits and vulnerabilities, weaknesses in the operating system or in the software. Therefore, this is important for low-level programming. Okay.
And also the OS protects the process code and data from each other. Normally a process cannot have access to another process memory except debugging a process by another process or using specific OS features such as create remote thread. OS protections, runtime address translation. The runtime address translation is to optimize memory usage of processes and also to protect the process data.
Okay, so there is process 1, virtual address space. It starts from 0 to until this. This is probably 4 GB. And there is process 2, virtual address space. It's from 0 to 4 GB. You see, they see as they have memory that is starting from 0 and up to 4 GB. And on the physical memory, they are assigned to different locations. Okay. And there is process key, virtual address space, and such. And this is done by the address translation. Okay. By the runtime address translation.
The virtual address space is separated into kernel and user space.
Okay, there is a kernel space. You see there are drivers, and there is user space. There are stacks, header code, data imports, stack, header code, data imports, and such. And there is also heaps of processes that are running in the user space.
OS protections, code vulnerabilities. The kernel space can be accessed through only specific OS APIs, e.g. in Windows using the native API, hardware protection CPU rings, see later.
Okay, there is vulnerability code in header code data imports. So if this part of the user space, header code data imports, can access the driver directly, then that would cause a lot of code vulnerability. Okay, so how this code, in that case, how can this code access the driver, the kernel space? it can access the driver by Windows native APIs, which are, for example, anti-DLL DLL or kernel-based DLL. You see, this code in that case sends command to this API, and this API access to the driver. Okay. This is same as having APIs in remote remote server, and you use those APIs to do such as authentication of your login having websites or your software and such. It is the same principle. Okay.
OS protections, software supported data execution prevention, DEP. The vulnerable code has no access directly to kernel space, but without DEP it can modify the code in the user space, even the OS API in user space, or can execute an attacker-placed malicious code.
Okay, so there is stack, data read write, and there is shared libraries, code read execute, and there is a heap, data segment, code segment, read write, read execute. These are the permissions of the code.
The OS can enforce DEP IENX always on settings on Windows.
Okay, let's see some more information related to DEP. Okay, this is from Microsoft's official website.
Data Execution Prevention (DEP) is a system-level memory protection feature that is built into the operating system starting with Windows XP and Windows Server 2003. DEP enables the system to mark one or more pages of memory as non-executable. Marking memory regions as non-executable means that code cannot be run from that region of memory, which makes it harder for the exploitation of buffer overruns. DEP prevents code from being run from data pages such as the default heap, stacks, and memory pools. If an application attempts to run code from a data page that is protected, a memory access violation exception occurs, and if the exception is not handled, the calling process is terminated. DEP is not intended to be a comprehensive defense against all exploits. It is intended to be another tool that you can use to secure your application.
Okay, also there is some more information. I think we have enough idea about the DEP now.
OS protections, address space layout randomization, ASLR.
We have seen this in the article we read at the beginning of the lecture on our Technica website. It was related to exploitation of iPhones and iPads.
Because of DEP, the attackers turned into code reuse. To prevent it, OS provides code randomization in the virtual address space.
Okay, so this is the first start, anti-DLL, kernel-based user 13, GDI 13, critical DLL, and that second start, user 13, GDI 13, kernel-based, and such. You see at the each start of the operating system, the memory address of the kernel space processes are changed, as you can see. Okay.
Increasing the entropy of ASLR makes brute forcing less effective. High entropy ASLR. Address space layout permutation ASLP. The place of the libraries are randomized as well as the order of the methods in the virtual address space. Code diversity OS protection. Multiple heaps and protected heap segments, e.g. late-free, MS Edge. Execute no read segments, XNR protection, hardware support later. Control flow integrity, observation of unintended use cases.
Okay, let's have some more information related to A, S, and R. And we have already seen this. Okay, so about effectiveness, we didn't read it.
Address space layout randomization is based upon the low chance of an attacker guessing the locations of randomly placed areas. Security is increased by increasing the search space. Thus, address space randomization is more effective when more entropy is present in the random offsets. Entropy is increased by either raising the amount of virtual memory area space over which the randomization occurs or reducing the period over which the randomization occurs. The period is typically implemented as small as possible, so most systems must increase VMA space randomization. To defeat the randomization, attackers must successfully guess the positions of all areas they wish to attack. For data areas such as stack and heap, where custom code or useful data can be loaded, more than one state can be attacked by using NOP slides for code or repeated copies of data. This allows an attack to succeed if the area is randomized to one of a handful of values. In contrast, code areas such as library base and main executable need to be discovered exactly. Often these areas are mixed, for example stack frames are injected onto the stack and a library is returned into.
Okay, so let's continue. Okay, we have seen the memory protection. Now the time is for CPU protection. So what options are available?
Protection rings. Hardware-supported data execution prevention.
Okay, so what is protection rings? Okay.
In computer science, hierarchical protection domains, 1, 2, often called protection rings, are mechanisms to protect data and functionality from faults by improving fault tolerance and malicious behavior by providing computer security. This approach is diametrically opposite to that of capability-based security. Citation needed.
Okay, so you see there is least privileged at the most outer ring, and then the privileges increases, and the kernel, the ring 0, has the most privilege.
Computer operating systems provide different levels of access to resources. A protection ring is one of two or more hierarchical levels or layers of privilege within the architecture of a computer system. This is generally hardware enforced by some CPU architectures that provide different CPU modes at the hardware or microcode level. Rings are arranged in a hierarchy from most privileged, most trusted, usually numbered 0, to least privileged, least trusted, usually with the highest ring number. On most operating systems, ring 0 is the level with the most privileges and interacts most directly with the physical hardware such as the CPU and memory. Special gates between rings are provided to allow an outer ring to access an inner ring's resources in a predefined manner, as opposed to allowing arbitrary usage. Correctly gating access between rings can improve security by preventing programs from one ring or privilege level from misusing resources intended for programs in another. For example, spyware running as a user program in Ring 3 should be prevented from turning on a web camera without informing the user, since hardware access should be a Ring 1 function reserved for device drivers. Programs such as web browsers running in higher numbered rings must request access to the network, a resource restricted to a lower numbered ring.
Okay, and there is hardware support data execution prevention. Let's read about it. Oh, this is the hardware step, I think.
Data Execution Prevention (DEP) is a set of hardware and software technologies that perform additional checks on memory to help protect against malicious code exploits. Hardware-enforced dep marks all memory locations in a process as non-executable unless the location explicitly contains executable code. A type of malicious code attacks tries to insert and run code from non-executable memory locations. dep helps prevent these attacks by intercepting them and raising an exception. This article describes the requirements for using hardware-enforced dep. This article also describes how to confirm that hardware dep is working in Windows.
Okay, so what requirements there are?
To use hardware-enforced dep, you must meet all the following conditions. Computer's processor must support hardware-enforced dep. Many recent processors support hardware-enforced dep. Both Advanced Micro Devices (AMD) and Intel Corporation have defined and shipped Windows-compatible architectures that are compatible with dep. This processor support may be known as NX (No Execute) or XD (Execute Disable) technology. To determine whether your computer's processor supports hardware-enforced dep, contact the manufacturer of your computer. Hardware-enforced dep must be enabled in the BIOS. On some computers, you can disable processor support for hardware-enforced dep in the BIOS. This support can't be disabled. Depending on your computer manufacturer, the option to disable this support may be labeled Data Execution Prevention (XD), Execute Disable, or NX. The computer must have Windows XP with Service Pack 2 or Windows Server 2003 with Service Pack 1 installed. Hardware-enforced dep must be enabled for programs on the computer. In 64-bit versions of Windows, hardware-enforced dep is always enabled for 64-bit native programs. However, depending on your configuration, hardware-enforced dep may be disabled for 32-bit programs.
Okay. Okay, this looks like still in research. You see there's a PhD thesis about this topic, as you can see. So I'm just going to read it from here.
Hardware-supported control flow integrity, not in use yet, e.g. Intel's control flow enforcement.
Let's look at this. Maybe this is available. There is a technical look from Intel. Oh.
Intel has a long history of working with the software community and making strides in strengthening protections of operating systems and software running on modern computer systems. As these protections came into effect, adversaries started looking for creative alternatives to bypass these protections. Return-oriented programming, also known as ROP, and jump-oriented programming, also known as JOP, are two such techniques that has been gaining popularity. JOP or ROP attacks can be particularly hard to detect or prevent because the attacker uses existing code running from executable memory in a creative way to change program behavior. What makes it hard to detect or prevent ROP, JOP is the fact that attacker uses existing code running from executable memory. Many software-based detection and prevention techniques have been developed and deployed with limited success. ROP is where the attacker relies on return instruction to stitch together a malicious code flow that was not programmer intended. Per the design, return instructions fetch the address of next instruction from stack, which was pushed on the stack by the prior call instruction, and executes instructions from that address. In the case of ROP-based attacks, the attacker a priori or at runtime scans for sequence of bytes in existing program code by scanning the program on disk or in memory. Figure 1 shows an example of existing instruction stream.
Okay. Okay, anyway, you can read about it if you want.
Intel SGX protecting memory regions from higher privileged access. Intel Software Guard Extensions (SGX) is a set of security-related instruction codes that are built into some modern Intel Central Processing Units (CPUs). They allow user-level as well as operating system code to define private regions of memory, called enclaves, whose contents are protected and unable to be either read or saved by any process outside the enclave itself, including processes running at higher privilege levels. 1. 2. SGX involves encryption by the CPU of a portion of memory. The enclave is decrypted on the fly only within the CPU itself, and even then, only for code and data running from within the enclave itself. 3. The processor thus protects the code from being spied on or examined by other code. 4. The code and data in the enclave utilize a threat model in which the enclave is trusted but no process outside it can be trusted, including the operating system itself and any hypervisor, and therefore all of these are treated as potentially hostile. The enclave contents are unable to be read by any code outside the enclave, other than in its encrypted form. 3. Applications running inside of SGX must be written to be side-channel resistant, as SGX does not protect against side-channel measurement or observation. 4. SGX is designed to be useful for implementing secure remote computation, secure web browsing, and digital rights management (DRM). 5. Other applications include concealment of proprietary algorithms and of encryption keys. 3.
Okay. Okay, I will take a pause. Okay. Reference monitor.
A reference monitor is any security model for enforcing an access control policy over subjects, e.g., processes, and users' ability to perform operations, e.g., read and write, on objects, e.g., files, memory, and sockets, on a system. The reference monitor must always be invoked. Complete mediation. The reference monitor must be tamper-proof. The reference monitor must be small enough to be subject to analysis and tests, the completeness of which can be assured, verifiable. The security kernel of an OS is a low-level, close to the hardware, implementation of a reference monitor.
Okay, so there is subject request access. Reference monitor checks and it denies or grants access to the object.
OS security kernel as reference monitor. Hierarchic security levels were introduced in x86 CPU architecture in 1985, Intel 80386.
Okay, 4 ordered privilege levels. Ring 0 highest, ring 3 lowest. Intended usage is like this. We have already seen this. So level 0 is operating system kernel, and level 1 and level 2 are operating system services, and level 3 are the applications that users use.
What happened to rings 1 and 2? It eventually became clear that the hierarchical protection that rings provided did not closely match the requirements of the system programmer and gave little or no improvement on the simple system of having 2 modes only. Rings of protection lent themselves to efficient implementation in hardware, but there was little else to be said for them. Opening square bracket ... closing square bracket ... This again proved a blind alley.
Okay, this is the words of Maurice Wilkes, 1994.
CPU protection ring structure from 2006. New ring -1 introduced for virtualization. Necessary for protecting hypervisor from VMs, virtual machines, running in ring 0. Hypervisor controls VMs in ring 0. Ring 0 is aka supervisor mode.
So ring -1 is hypervisor mode, ring 0 is kernel mode, Unix root, WinADM. Ring 1 not used, ring 2 not used, ring 3 is user mode. So this is introduced in 2006 and there is privileged instructions.
Some of the system instructions, called privileged instructions, are protected from use by application programs. The privileged instructions control system functions, such as the loading of system registers. They can be executed only when the privilege level is 0 or -1, most privileged. If one of these instructions is attempted when the privilege level is not 0 or -1, then a general protection exception, #GP, is generated, and the program crashes. Principle of protection ring model. A process can access and modify any data and software at the same or less privileged level as itself. A process that runs in kernel mode, ring 0, can access data and SW in rings 0, 1, 2 and 3 but not in ring -1.
Okay, so within their ring level they can access or modify, so software and data are in the same ring. And there is data in ring 2 and there is software in ring 1. So the software in ring 1 can modify and access the data and software in ring 2 and ring 3, but ring 2 cannot access to ring 1. And ring 0 same, and ring -1 is same principle.
The goal of attackers is to get access to kernel or hypervisor mode through exploits, by tricking users to install software. User processes access to system resources. User processes need to access system resources, memory and drivers. User application processes should not access system memory directly, because they could corrupt memory. The CPU must restrict direct access to memory segments and other resources depending on the privilege level, current privilege level, corporal.
Actually, this is CPL.
Question 1. How can a user process execute instructions that require kernel mode, e.g. for writing to memory? Answer. The CPU must switch between privilege levels. Question 2. How should privilege levels be switched? Answer. Through controlled invocation of code segments. Controlled invocation of code segments.
Okay, so there is ring 3 code segment of user processes. It calls a gate, and then gate calls kernel code segments, and there is driver code segments and hypervisor code segments. Then kernel code segment returns value to call gate, and it returns value to code segment of user process. It is like accessing something from an API.
Controlled invocation. The user process executes code in specific code segments. Each code segment has an associated mode which dictates the privilege level the code executes under. Simply setting the mode of user process code to kernel would give kernel privilege to user process without any control of what the process actually does. Bad idea. Instead, the CPU allows the user process to call kernel code segments that only execute a predefined set of instructions in kernel mode, and then returns control back to the user process code segment in user mode. We refer to this mechanism as controlled invocation.
Okay, it's pretty clear.
Hardware-supported data execution prevention. Intel processors with XD support. AMD processors with NX support. Hardware-enforced DEP marks all memory locations as non-executable. You cannot execute code in this portion of memory unless the location explicitly contains executable code. Hardware-enforced DEP relies on processor hardware to mark memory with an attribute that indicates that code should not be executed from that memory. Processors that support hardware-enforced DEP are capable of raising an exception when code is executed from a memory location where it should not be executed. To use these processor features, the processor must run in physical address extension (PAE) mode. HP ships Windows XP with PAE enabled. Control flow enforcement in plan. Processors will directly support shadow call stack tracking. Method return addresses are stored in data stack and the shadow stack too. Shadow stack is not accessible. The processor checks the return addresses. If there's unmatching return, then control protection exception is raised. Processors also support indirect branch tracking. After each legitimate indirect branch instruction, the code must contain a NOP-like special instruction. If the program execution is redirected by an attacker, the NOP-like instruction is missing and a control flow protection error is raised.
Okay, it was announced in June 2016. Let's see if it is effective or release it. Okay, there is a news from Intel in 2020 June 15. Okay, so it is available in Tiger Lake CPU, I suppose.
Intel control flow enforcement technology available in Tiger Lake adds CPU-level protection against a common class of malware.
Let's read this.
The security of our customers' data is a top priority at Intel. As part of Intel's Security First pledge, our engineers continue to deliver advancements to help safeguard our technology from evolving cyber threats. It begins with designing and engineering security features into our products and continues in our work with the industry to move security innovation forward. Today, we are announcing a new security capability. Intel Control Flow Enforcement Technology, Intel SET, will be first available on Intel's upcoming mobile processor code named Tiger Lake. Intel SET delivers CPU-level security capabilities to help protect against common malware attack methods that have been a challenge to mitigate with software alone.
Okay, so you see it was announced in 2016 and it is getting released in earliest at the 2020, so it took at least 4 years to get into market.
Intel SET is designed to protect against the misuse of legitimate code through control flow hijacking attacks, widely used techniques in large classes of malware. Intel SET offers software developers two key capabilities to help defend against control flow hijacking malware: indirect branch tracking and shadow stack. Indirect branch tracking delivers indirect branch protection to defend against jump, call-oriented programming (JOP/COP) attack methods. Shadow stack delivers return address protection to help defend against return-oriented programming (ROP) attack methods. These types of attack methods are part of a class of malware referred to as memory safety issues, and include tactics such as the corruption of stack buffer overflow and use after free. For technical details, see a technical look at Intel's control flow enforcement technology.
Okay, so there is a link, and when I click it, okay, it opens this page, and we have already seen this page, by the way.
According to Trendmicro's Zero-Day Initiative (ZDI), 63.2% of the 1,097 vulnerabilities disclosed by ZDI from 2019 to today were memory safety related. These malware types target operating systems (OS), browsers, readers, and many other applications. It takes deep hardware integration at the foundation to deliver effective security features with minimal performance impact. Intel was the first to tackle these complex security challenges, and we remain committed to working with the industry to drive security innovation. We recognize that scaling OS and application adoption to truly solve the problem would require industry-wide collaboration. To accelerate adoption, we published the Intel set specifications in 2016. Additionally, Intel and Microsoft have been working closely to prepare Windows 10 and developer tools so applications and the industry at large can offer better protection against control flow hijacking threats.
Okay, so you see our lecture is already containing information about this, and at that time the lecture was prepared, it was unknown, but it is announced and getting to market at the moment.
As more proactive protections are built into the Windows OS, attackers are shifting their efforts to exploit memory safety vulnerabilities by hijacking the integrity of the control flow, said David Weston, Director of Enterprise and OS Security at Microsoft. As an opt-in feature in Windows 10, Microsoft has worked with Intel to offer hardware-enforced stack protection that builds on the extensive exploit protection built into Windows 10 to enforce code integrity as well as terminate any malicious code.
Okay, so there's a picture about this Intel control. Okay, 1 second. Let's open this. Okay, so this is a pretty big picture. So Intel set equals to indirect branch tracking IBT plus shadow stack SS. And indirect branch tracking IBT. IBT, there is indirect branch protection to defend against jump call. Okay, we have seen this. So in program in memory, call asterisk %RDX and branch and add rux RBX. Intel set will help prevent attackers from jumping to arbitrary addresses. Okay, so this will prevent jumping to arbitrary address, a certain address. I think it is pretty clear. Shadow stack SS delivers return address protection to defend against return-oriented program group. Return to point 1, which it will return to 2. Intel set will help block or call if return addresses on both stacks don't match. Oh, okay. So you won't be able to return a stack on shadow if it is not matching. Okay. Oh, sorry, we have closed our slide. Okay. Okay, let's continue. So this is explaining the plan.
Control flow enforcement in plan. Processors will directly support shadow call stack tracking. Method return addresses are stored in data stack and the shadow stack too. Shadow stack is not accessible. The processor checks the return addresses. If there's unmatching return, then control protection exception is raised.
Okay, we have read this Intel Software Guard extension. And let's see what is this. I need to make this English. Okay.
What is Intel SGX? There is tremendous opportunity for application and solution developers to take charge of their data security using new hardware-based controls for cloud and enterprise environments. Intel Software Guard Extensions Intel SGX 1.2 offers hardware-based memory encryption that isolates specific application code and data in memory. Intel SGX allows user-level code to allocate private regions of memory, called enclaves, which are designed to be protected from processes running at higher privilege levels. Only Intel SGX offers such a granular level of control and protection.
As today's online threats become increasingly more sophisticated, it's become critical to maintain the security of application data. From medical and confidential information to biometric factors, passwords, secrets, data protection, and intellectual property, one of the best ways to protect your and your customers' data is to secure it while being processed in memory. Intel Software Guard Extensions, or Intel SGX for short, helps developers do just that. With the ability to create encrypted enclaves that help safeguard select information and program code while they are in use, Intel SGX is designed to ensure application integrity and confidentiality, protect execution, and help keep your data protected.
Okay. So let's continue.
TCB, Trusted Computing Base. The trusted computing base (TCB) of a computer system is the set of all hardware, firmware, and/or software components that are critical to its security, in the sense that bugs or vulnerabilities occurring inside the TCB might jeopardize the security properties of the entire system. By contrast, parts of a computer system outside the TCB must not be able to breach the security policy and may not get any more privileges than are granted to them in accordance to the security policy. From TCSEC Trusted Computer Evaluation Criteria, 1985.
Okay, so we separate components as to two categories.
TCB security relevant components.
And
Components that are irrelevant for security.
okay, and let's see if there is more information related to this.
The trusted computing base (TCB) of a computer system is the set of all hardware, firmware, and/or software components that are critical to its security, in the sense that bugs or vulnerabilities occurring inside the TCB might jeopardize the security properties of the entire system. By contrast, parts of a computer system outside the TCB must not be able to misbehave in a way that would leak any more privileges than are granted to them in accordance to the security policy. The careful design and implementation of a system's trusted computing base is paramount to its overall security. Modern operating systems strive to reduce the size of the TCB not verified in body so that an exhaustive examination of its code base by means of manual or computer-assisted software audit or program verification becomes feasible.
Okay, there is some more information. And platform virtualization, which is very commonly used in today's IT.
Platform virtualization. Hypervisor, aka VMM, Virtual Machine Monitor, is needed to manage multiple guest OS's virtual machines in the same hardware platform.
I bet you have heard about VPS and renting a VPS. They are all done with virtualization, basically on a dedicated server. You can have as many as virtual private servers. They are completely separated from each other and from the host environment. So a hacking or an exploit that happens inside one of the virtual windows cannot affect the other virtual computers. It is a great feature, great technology.
Many types of hypervisors available.
VMware, which I also use a lot.
VMware is most known commercial product Type 1 and 2. Free version comes with a limitations.
VirtualBox, which is also very popular.
VirtualBox is a hypervisor for x86 virtualization. It is freely available under GPL Type 2. Runs on Windows, Linux, OS X and Solaris hosts.
Okay, we will see about what are these types. So this is type 1 and 2, this is type 2. And Hyper-V.
Hyper-V is Microsoft's hypervisor technology, Type 1.
But it
Requires Windows Server.
I think it is also available in Windows 10. Let's check it out on Turn Windows Features, and yes, on Windows 10 there is also Hyper-V platform.
Xene, powerful open source hypervisor, Type 1.
Okay, so Type 1 is, you see, native.
Type 1 VM architecture, native.
Okay, so there are applications on virtual machines, and you see virtual machines are separated like this. Guest operating system, VM, e.g. macOS. So you can run 3 virtual machines at the same time. One of them can run Windows, one of them can run Linux, one of them can run macOS, and whatever you want. There is hypervisor, which is under these virtual machines, and there is hardware. So basically, hardware is the lowest level, hypervisor is the upper level, and there are virtual machines, and above them there are applications.
No host OS.
So you see, if you are running with a hypervisor native, it is running directly on
Hypervisor runs directly on hardware. High performance.
There is no hosting operating system for hypervisor.
Traditionally limited GUI, but is improved in modern versions.
GUI is the graphical user interface.
HW support can be an issue.
Hardware support can be an issue. So Type 2, which is hosted.
Type 2 VM architecture, hosted.
So you see there is hardware, and above it there is host operating system. So basically Type 2 is running on the host operating system. However, Type 1 is running on the hypervisor, which is directly running on the hardware. So there is no hosting operating system for hypervisor. However, on Type 2 there is hosting operating system. For example, Windows, Linux, macOS or whatever, and above it there is hypervisor. Okay.
Hypervisor runs on top of host OS. Performance penalty, because hardware access goes through 2 OSs. Traditionally good GUI. Traditionally good HW support, because host OS drivers available.
Okay.
Challenges of running VMs. VMs and apps in a VM must not know that hypervisor exists or that they share HW resources with other VMs. Hypervisor must protect VM's memory areas from each other. Hypervisor must protect it itself from all VMs. Hypervisor must present virtual hardware interface to VMs.
You see, this is really important. Hypervisor must protect itself from all VMs, and hypervisor must protect VMs memory areas from each other, because an exploit and a hacking in one of the virtual machine can affect other virtual machines, or worse, the hosting operating system or hosting device. Therefore, the separation of the private servers and encapsulation of them is extremely important and critical. Okay. So,
Type 1 VM architecture ring allocation.
in the type 1, which is native virtual machines, there is hardware, and above it there is ring -1, and above it there is ring 0, and above it there is ring 3, which are the regular applications.
Guest OS VMs are less privileged than the hypervisor. Hypervisor is well protected from the VMs. Good performance and good security.
And in the type 2, it is like this.
Type 2 VM architecture ring allocation.
So there is hardware, and the ring 0 is hosting operating system, which is Windows, Linux, or MacOS. And above it there is hypervisor. You see, hypervisor and virtual machines are running in the same ring. Therefore, it is harder to keep the security, because they're in the same level. They can access each other's processors. Therefore, it is harder to keep the security.
Guest OS VMs run in ring 3. Guest OS VMs call privileged instructions that are forbidden in ring 3. Forbidden instructions cause exceptions that are handled by interrupt exception handler to be executed. Slow performance. Platform virtualization products.
Okay, so there are type 1 native and type 2 hosted. Native 1 natives are Microsoft Hyper-V, VMware ASX. I have never used VMware ASX. Let's read about it.
VMware ESXi, the purpose-built bare metal hypervisor. Discover a robust, bare metal hypervisor that installs directly onto your physical server. With direct access to and control of underlying resources, VMware ESXi effectively partitions hardware to consolidate applications and cut costs. It's the industry leader for efficient architecture, setting the standard for reliability, performance, and support.
Okay, so what ASXi delivers?
What ESXi delivers: IT teams are under constant pressure to meet fluctuating market trends and heightened customer demands. At the same time, they must stretch IT resources to accommodate increasingly complex projects. Fortunately, ESXi, formerly known as ESX, helps balance the need for both better business outcomes and IT savings. VMware ESXi enables you to consolidate hardware for higher capacity utilization, increase performance for a competitive edge, streamline IT administration through centralized management, reduce CapEx and OpEx, minimize hardware resources needed to run the hypervisor, meaning greater efficiency.
Okay, so there is two other terms, which are CapEx and OpEx. So CapEx and OpEx, what are they? Okay. I think there is a problem with my internet connection.
Capital expenditure or capital expense, CapEx or CapEx, is the money an organization or corporate entity spends to buy, maintain, or improve its fixed assets, such as buildings, vehicles, equipment, or land. 1. 2. It is considered a capital expenditure when the asset is newly purchased or when money is used towards extending the useful life of an existing asset, such as repairing the roof. 3.
Okay, and there is OpEx.
An operating expense, operating expenditure, operational expense, operational expenditure or OPEX is an ongoing cost for running a product, business, or system. 1. Its counterpart, a capital expenditure, CapEx, is the cost of developing or providing non-consumable parts for the product or system. For example, the purchase of a photocopier involves CapEx, and the annual paper, toner, power and maintenance costs represents OPEX. 2. For larger systems like businesses, OPEX may also include the cost of workers and facility expenses such as rent and utilities.
Okay, and there is Citrix Zen Server, Oracle VM Server, Amazon EC2, IBM System Z Hypervisor. There is Microsoft Visual PC, VMware Workstation, which probably a lot of you have already used it. VMware Workstation, it's a great software. I also use it for virtual machines, and it really provides high performance and security, I believe. Let's read about it. Okay, I am not able to select the text. Anyway, Citrix Zenslide and VirtualBox. VirtualBox is also very popular. However, it is very weak in terms of features. Okay, let's see operating system level virtualization. Okay, we have already seen this. There is infrastructure at the very bottom, and in type 1 there is operating system, Docker engine. This was containers and these are virtual machines. Each virtual machine includes the application, the necessary binaries and libraries, and entire request operating system, all of which may be tens of gigabytes in size. And if you use containers include the application and all its dependencies, but share the kernel with other containers. I see. They run as an isolated process in the user space on the host operating system. They are also not tied to any specific infrastructure. Docker contains runs on any computer and on any infrastructure and in any cloud. Okay. So virtual machines versus containers, if we search for that, we may get a clearer idea. Okay, let's see the difference. Okay, there is official document on Microsoft.
Containers versus virtual machines. This topic discusses some of the key similarities and differences between containers and virtual machines (VMs), and when you might want to use each. Containers and VMs each have their uses. In fact, many deployments of containers use VMs as the host operating system rather than running directly on the hardware, especially when running containers in the cloud. Container architecture. A container is an isolated, lightweight silo for running an application on the host operating system. Containers build on top of the host operating system's kernel, which can be thought of as the buried plumbing of the operating system, and contain only apps and some lightweight operating system APIs and services that run in user mode, as shown in this diagram.
Okay, so there is hardware kernel and app services, and in a container it is like app services, and in a container it's like apps and services. And in virtual machine,
In contrast to containers, VMs run a complete operating system including its own kernel as shown in this diagram.
So you see in virtual machine there are different kernels. However, in the container approach, they use the same kernel as the operating system kernel.
Containers versus virtual machines. The following table shows some of the similarities and differences of these complementary technologies. Feature virtual machine container.
Okay, so from isolation feature, virtual machine
Provides complete isolation from the host operating system and other VMs. This is useful when a strong security boundary is critical, such as hosting apps from competing companies on the same server or cluster.
and for containers.
Typically provides lightweight isolation from the host and other containers, but doesn't provide as strong a security boundary as a VM. You can increase the security by using Hyper-V isolation mode to isolate each container in a lightweight VM.
From operating system feature,
Runs a complete operating system including the kernel, thus requiring more system resources, CPU, memory, and storage. Runs the user mode portion of an operating system, and can be tailored to contain just the needed services for your app, using fewer system resources.
from guest compatibility,
Runs just about any operating system inside the virtual machine. Runs on the same operating system version as the host. Hyper-V isolation enables you to run earlier versions of the same OS in a lightweight VM environment.
from deployment point,
Deploy individual VMs by using Windows Admin Center or Hyper-V Manager. Deploy multiple VMs by using PowerShell or System Center Virtual Machine Manager. Deploy individual containers by using Docker via command line. Deploy multiple containers by using an orchestrator such as Azure Kubernetes Service.
and operating system updates and upgrades.
Download and install operating system updates on each VM. Installing a new operating system version requires upgrading or often just creating an entirely new VM. This can be time-consuming, especially if you have a lot of VMs. Updating or upgrading the operating system files within a container is the same. Edit your container image's build file, known as a Docker file, to point to the latest version of the Windows base image. Rebuild your container image with this new base image. Push the container image to your container registry. Redeploy using an orchestrator. The orchestrator provides powerful automation for doing this at scale. For details, see tutorial, update an application in Azure Kubernetes Service.
Okay, about persistent storage.
Use a virtual hard disk (VHD) for local storage for a single VM, or an SMB file share for storage shared by multiple servers.
Okay, for containers.
Use Azure disks for local storage for a single node, or Azure Files (SMB) shares for storage shared by multiple nodes or servers.
About load balancing.
Virtual machine load balancing moves running VMs to other servers in a failover cluster. Containers themselves don't move, instead an orchestrator can automatically start or stop containers on cluster nodes to manage changes in load and availability.
About fault tolerance.
VMs can fail over to another server in a cluster, with the VM's operating system restarting on the new server. If a cluster node fails, any containers running on it are rapidly recreated by the orchestrator on another cluster node.
From networking point.
Uses virtual network adapters. Uses an isolated view of a virtual network adapter, providing a little less virtualization. The host's firewall is shared with containers while using less resources. For more, see Windows Container Networking.
Okay, let's continue. I will take a pause. Okay, continuing.
Hardware support for virtualization. Modern Intel and AMD x86 CPUs support virtualization. Intel VT, Intel Virtualization Technology. AMD V, AMD Virtualization. Must be enabled in BIOS. Can be enabled and disabled. Computers with single OS typically have virtualization disabled. Access to data and code segments for hypervisor can be restricted to processes running in hypervisor mode. Some instructions are reserved for hypervisor mode.
You should enable virtualization because in today's softwares, there are many software that uses virtualization technology, such as emulators. Okay, so if you enable virtualization, your emulator will likely to have work in much better performance and much better efficiency. Okay. Okay.
Why use platform virtualization? Efficient use of hardware and resources. Improved management and resource utilization. Saves energy. Improved security. Malware can only infect the VM. Safe testing and analysis of malware. Isolates VMs from each other. Distributed applications bundled with OS. Allows optimal combination of OS and application. Ideal for cloud services. Powerful debugging. Snapshot of the current state of the OS. Step through program and OS execution. Reset system state. Hypervisor examples of use. Cloud providers run large server parks. Each customer gets its own VM. Many customers share the same hardware. Migrated VMs between servers to reduce capacity. Amazon EC2 Data Center.
Okay. Not this one. You see how big is the data center. Okay, there is read more. Okay. This is a computer graphic of the data center, but it's probably like this. Okay.
Testing and software analysis. Potentially damaging experiments can be executed in isolated environment. Take a snapshot of the current state of Theos. Use this later on to reset the system to that state. Malware analysis. Trusted computing. Trusted computing motivation. Software alone cannot be trusted. Malware infection in OS kernel remains undetected by anti-malware tools. Physical access to computers opens up for attacks that can circumvent traditional TCBs, trusted computing base, e.g. secure operating systems. Remote parties do not know the status of systems they are communicating with. Remote parties do not know the physical identity of hosts they are communicating with. Basic idea of trusted computing. Use specialized security hardware as part of TCB in a computer system. cannot be compromised by malware, can verify the integrity of OS kernel, can make physical tampering difficult, can report status of system to remote parties, can report identity of system to remote parties. Gives increased level of trust that the system will perform as expected, specified.
So you see, use specialized security hardware. For trusted computing, we use specialized security hardware.
What is trust in the sense of TC? To have confidence in assumptions about security. Trust is to believe that security assertions will hold. A trusted component, operation, or process is one whose behavior is assumed to be correct under any operating condition, and which is assumed to resist subversion by malicious software, viruses, and manipulations. A trusted component enforces the security policy as long as these assumptions hold. A trusted component violates the security policy if it breaks. Q1. How do you know that a component is trustworthy, i.e. that it will not break? A1. Through assurance. Q2. Trusted by whom to do what? Trusted by user, by vendor, or by third party, NSA. What if they have conflicting interests? Characteristics of trusted hardware. Physically secure hardware component. Assumed not to break because it's hardware. Environmental monitoring, temperature, power supply, structural integrity. Tamper responsive. Implementations.
CPU, ROM for OS and application code. So what was ROM, if you don't remember? It is read-only access memory, and let's read about it.
Read-only memory, ROM, is a type of non-volatile memory used in computers and other electronic devices. Data stored in ROM cannot be electronically modified after the manufacture of the memory device. Read-only memory is useful for storing software that is rarely changed during the life of the system, also known as firmware. Software applications, like video games, for programmable devices can be distributed as plug-in cartridges containing ROM. Strictly, read-only memory refers to memory that is hardwired, such as diode matrix or a mask ROM integrated circuit (IC), which cannot be electronically changed after manufacture. Although discrete circuits can be altered in principle through the addition of baud wires and/or the removal or replacement of components, ICs cannot. Correction of errors, or updates to the software, require new devices to be manufactured and to replace the installed device.
Okay.
Specialized hardware for cryptography and for storing secrets. Trusted hardware, example. IBM 4765 Secure Coprocessor.
Okay, so it is coprocessor, as you can see. Tamper responding members, shields, PCI board security, circuitry, and sensors. Let's look about this in the Google. Okay, there is Wikipedia.
The IBM 4765 1 PCIe cryptographic coprocessor 2 is a hardware security module (HSM) that includes a secure cryptoprocessor implemented on a high-security, tamper-resistant, programmable PCIe board. Specialized cryptographic electronics, microprocessor, memory, and random number generator housed within a tamper-responding environment provide a highly secure subsystem in which data processing and cryptography can be performed. The IBM 4765-3 is validated to FIPS Pub 140-2 Level 4, the highest level of certification achievable for commercial cryptographic devices. The IBM 4765 Data Sheet 4 describes the coprocessor in detail. IBM supplies 2 cryptographic system implementations. The PKCS number 11.5 implementation creates a high-security solution for application programs developed for this industry standard API. The IBM Common Cryptographic Architecture (CCA) implementation provides many functions of special interest in the finance industry, extensive support for distributed key management, and a base on which custom processing and cryptographic functions can be added.
Okay. You see, trusted computing is different than trusted computing base. We have already seen it.
Trusted Computing (TC) is a technology developed and promoted by the Trusted Computing Group. 1. The term is taken from the field of trusted systems and has a specialized meaning. With trusted computing, the computer will consistently behave in expected ways, and those behaviors will be enforced by computer hardware and software. 1. Enforcing this behavior is achieved by loading the hardware with a unique encryption key inaccessible to the rest of the system. TC is controversial as the hardware is not only secured for its owner, but also secured against its owner. Such controversy has led opponents of trusted computing, such as free software activist Richard Stallman, to refer to it instead as treacherous computing, even to the point where some scholarly articles have begun to place scare quotes around trusted computing. 4. Trusted computing proponents such as International Data Corporation, 5, the Enterprise Strategy Group, 6, and Endpoint Technologies Associates, 7, claim the technology will make computers safer, less prone to viruses and malware, and thus more reliable from an end-user perspective. They also claim that trusted computing will allow computers and servers to offer improved computer security over that which is currently available. Opponents often claim this technology will be used primarily to enforce digital rights management policies and not to increase computer security. 2.8.23. Chip manufacturers Intel and AMD, hardware manufacturers such as HP and Dell, and operating system providers such as Microsoft include trusted computing in their products if enabled. 9.10. The U.S. Army requires that every new PC it purchases comes with a Trusted Platform Module (TPM). 11.12. As of July 3, 2007, so does virtually the entire United States Department of Defense. 13.
Okay, so there are key concepts, and which are
Trusted computing encompasses 6 key technology concepts, of which all are required for a fully trusted system, that is, a system compliant to the TCG specifications. Endorsement: key secure input and output memory curtaining, protected execution sealed storage remote attestation trusted third party TTP.
okay, so you see each one of them have different explanations. And let's continue to our slide.
Trusted Computing Group TCG History and Evolution. October 1999, TCPA formed. Trusted Computing Platform Alliance. Founders: IBM, HP, Compaq, Intel and Microsoft. 2001-1 Street TPM specification released. Trusted Platform Module. 2002, TCPA changes its name to TCG. Trusted Computing Group. Industry Standards Organization. 2003 TCPA TPM Spec. Adopted by TCG as TPM 1.2. 2012 Draft TPM Specification 2.0 published. TPM 2.0 Spec. Not compatible with TPM 1.2 Spec. 2015 Official TPM Specification 2.0. Pervasiveness of the TPM.
Okay, there's CPU, RAM, chipset, display, BIOS, TPM, onboard devices, removable devices.
The TPM chip sits on the motherboard. Installed in 2 billion devices per 2015. Relatively obscure technology for most people.
So there is TPM functionality. I think it was on Wikipedia as well. Okay, here. So what functionality it has?
Trusted Platform Module provides a hardware random number generator, 5-6 facilities for the secure generation of cryptographic keys for limited uses. Remote attestation creates a nearly unforgeable hash key summary of the hardware and software configuration. The software in charge of hashing the configuration data determines the extent of the summary. This allows a third party to verify that the software has not been changed. Binding encrypts data using the TPM bind key, a unique RSA key descended from a storage key. Clarification needed. 7. Sealing, similar to binding, but in addition, specifies the TPM state. Clarification needed for the data to be decrypted, unsealed. 8. Other trusted computing functions.
I think Windows 10 has TPM features.
Automated provisioning in the TPM reduces the cost of TPM deployment in an enterprise. New APIs for TPM management can determine if TPM provisioning actions require physical presence of a service technician to approve TPM state change requests during the boot process. Anti-malware software can use the boot measurements of the operating system start state to prove the integrity of a computer running Windows 10 or Windows Server 2016. These measurements include the launch of Hyper-V to test that datacenters using virtualization are not running untrusted hypervisors. With BitLocker Network Unlock, IT administrators can push an update without concerns that a computer is waiting for PIN entry.
Okay, these are some complex things. If you are interested in them, you can read about them. Okay, so TPM usage.
TPM is both the name of a standard and a chip. TPM chip at the heart of hardware, software approach to trusted computing.
Okay. Not this one, not this one. Oh. Okay. Okay, there's a question asked on Community Intel. Oh, it's gone. Anyway, let's continue.
Current TPM chips implement TPM Spec 2.0. Latest version of TPM Spec 2.0 is from 2015. TPM chip mounted on motherboard. TPM equipped computing platforms. Laptops, servers, pads, mobile phones. Used by software platforms. Windows Vista, the 8th of July 10, Linux, and Mac OS. Supports 3 basic services. Authenticated, measured boot, sealed storage, encryption, remote attestation. Boot protection. BIOS UEFI, loaded by processor code at power on. BIOS UEFI initializes and identifies system devices such as display and keyboard. BIOS UEFI then loads software OS held on a peripheral device such as a hard disk. BIOS UEFI firmware is stored in ROM. Boot protection, CRTM, core root of trust for measurement. Boot protection focuses on verifying the integrity of the OS during boot. CRTM can provide integrity assurance of OS. The usage of CRTM can be to check PCR or to check digital signatures of software. Boot protection with TPM. The CRTM is the initial code which starts running at CPU power on. The boot integrity depends on the CRTM integrity. Multiple options for storing the CRTM, e.g. in CPU or external ROM. Multiple options for storing PCR, e.g. in TPM or in other ROM chip.
Okay, so there is CRTM options. It checks processor code, measure, check PCR, BIOS, measure, check PCR. OS kernel check PCR, measure drivers, PCR, platform configuration registers, hash values of known good software modules stored in TPM or CPU.
Boot protection with UEFI. Unified Extensible Firmware Interface replaces BIOS. The CRTM is the UEFI code which starts at CPU power on. The boot integrity depends on the UEFI CRTM integrity. The root public key must be stored in CPU.
UEFI is the new standard technology of BIOS. New motherboards usually have UEFI, not BIOS anymore. Okay.
2 modes of boot protection. Secure boot with UEFI, not with TPM. See UEFI later. The platform owner can define expected trusted measurements hash values of OS software modules. Hash values stored in memory signed by private PK platform key. Public PK stored in secure firmware on platform measured has values can be compared with stored values. Matching measurement values guarantee the integrity of the corresponding software modules. Boot process terminates if a measurement does not match the stored value for that stage of the boot process. Authenticated, measured boot with TPM. Records measured values in PCRs and reports to remote party. Does not terminate boot if measured values are wrong. Sealed storage, encryption. Encrypts data so it can be decrypted by a certain machine in given configuration. Depends on. Storage root key, SRK, unique to machine. Decryption only possible on unique machine. Can also extend this scheme upward. Create application key for desired application version running on desired system version. Supports disk encryption. Remote attestation. TPM can certify configuration to others, with a digital signature in configuration info, giving another user confidence in it, based on attestation key, AK. Remote parties can validate signature based on a PKI, provides hierarchical certification approach, trust TPM, then trust the OS, then trust applications.
Okay, system attestation about platform identity and software status, remote party, and so on. If you are interested in any of these technologies, you can look for more information on the internet. I think this is enough for today's lecture. Hopefully see you next week. There was a keyword error, by the way. Okay. And I will upload the slide to our GitHub repository. Okay, end of lecture. Hopefully see you next week.